Hello, my name is Peter Cross. Welcome to our website and this presentation of digital methods time measurement, or digital MTM for short. My association with MTM goes back more years than I care to remember. As an instructor member with the UK MTM Association, I trained many hundreds of practitioners in both MTM-1 and MTM-2 between the years 1968 and 1973. It therefore saddens me to witness the continuing decline of both application and training in the MTM system over recent years. This information is a summary of data recently published by the IMD. You can see that worldwide training has dropped by 74% in the 50 years since 1964, whereas in the UK, over the same 50-year period, training has dropped from an average of 700 per annum to 45 per annum, a drop of more than 90%. One can conclude therefore that the application of MTM in the UK is virtually non-existent. In consequence, MTM practitioner training is now prohibitively expensive. The use of motion analysis software is not commonplace, and motion analysis software that is available is either very expensive or lacks functionality. For these reasons, some time ago I decided it was time that MTM was brought into the 21st century. In essence, this meant representing both the application and the training of MTM within a digital foundation. This digital foundation, or database as more commonly known, interfaces with computer software. The software was designed specifically to deliver a more efficient and therefore a more cost-effective method of practitioner training. In addition to this, a unique suite of motion analysis software has been added to the package, which I guarantee will dramatically reduce the application costs of MTM. In this video, we examine the methods and the analytical procedures used to create a digital foundation from which any high-level MTM system can be created. During the course of the video, we calculate digital values for both MTM-2 and for MTM-UAS. Each of the values created will have both a mean TMU value and also a variance. The benefit of knowing the variance of each TMU value within the analysis will be demonstrated during the latter part of this video. I'll try to keep the presentation simple. I'll also try to speak as clearly as possible and hope that my Brummie accent doesn't cause too much difficulty. So okay, grab a cup of coffee and let's get going. Here we have the MTM-2 project report, which is shown as a PDF document. MTM-2 was released in 1965. This report was published in June 1971. MTM-1 data have been extracted from a huge amount of motion analyses, which was taken from a very diverse range of industries across the USA, Europe and Scandinavia. You will see just how comprehensive and detailed it is. You can see it extends to over 40 pages, and there's a very elaborate set of graphs, tabulations, etc., plus very detailed explanation of the thinking behind the structure of MTM-2, what the various options were, why they decided to select one type of algorithm as opposed to another one, and so it goes on. Okay, we're now at an Excel file, standard Excel file, and you will see along the bottom there's about 10 or 11, I think there's 11 separate tabs of information which were extracted from the MTM-2 project report. This first one is a fundamental one. It's the structure of the MTM motions. I think it's fairly clear the way it's laid out. Get, for example, the frequency, FRQ, is the frequency of occurrence of that particular motion in the 71 project report, MTM-2 project report. It gives the case of reach and the particular case of grasp. You look at the PA, for example, you've got what? Over 3,000. So you've got well over 30% of the motions under put, case A put. And again you've got case A, case B and case C moves, and the frequencies mostly being, as you can see, case B, which you'd expect. And then looking at these final motions, which again are fairly significant, they account for about 20-25% of all the motions. You've got apply pressure, crank, eye action, regrasp. That surprised me. 400 nod. Limiting regrasps, quite a high number. ENW is get weight and put weight. I propose we deal with that separately, or differently rather, and we'll explain that later. Foot motion, step, and this bend and arise figure is an estimate of. We couldn't pick any up in the project report. I don't know whether they were just missed out accidentally, but I mean there must have been some bend and arising, in there. But so I'll put an estimate in of 30. That may well be wrong. It could be 50, it could be 100. I don't think it's any more than 100. But we know, I mean, it's there. We can always modify that at some stage if we find that that's insignificant or needs to be changed. But it doesn't affect the overall calculations of MTM-2 codes, because obviously it's a separate motion anyway. And we have a total of 8,009, whatever it is, 8,700. I thought it was higher than that, never mind. Oh, I know why. There's no disengaging. The disengaged motion, I think there's about 142, and there's an argument for including disengaged, but it's not in the project, and that's the total number of motions they've got there. So that's a fundamental set of data, which again is very important, because knowing all the MTM-1 values for these components, you can calculate the average motion for any one of those codes. But the only problem is you realise that there's no distances in there, and the distances is covered in this second tab. This is the table showing the distribution of distance for each of the codes and the cases of reach or move. This looks a little bit overwhelming when you first look at it, but when you get used to it, it's fairly straightforward. Down the left hand side you've got the distance of the move, the reach of the move. In this case the distance is 1, 2, 4, all the way up to 80, I think, 80 being the maximum distance. So that is purely the distance straight off the MTM-1 data card. And for example, with PA, you've got 10% of the motions are 1 centimetre or less. 10:15. So looking at this first motion, this first PA, you've got what, 15, was it 45, 35% all fall within the first distance category, PA5. Okay, we're now looking at the MTM variance table within the database. It crystallizes the two previous tables we saw, the motion frequency table, where you see each of the motion codes and the relative frequencies amounting to about 9,000 odd records, and then we saw the distance distribution of those records across the various codes. This table pulls together both sets of data into one master table, from which we can generate the MTM-2 codes and the UAS codes for that matter. But looking at the PBs, where there is a parameter, which is the P1SE or the P1SSE, we go across, that's the case, it's always a case C move, that's the distance, 6. The next one is the VL, which is the value of that move. At case C, 6 centimetre move is a value of whatever, 5.6. The parameter value of that P1SSE is 9.1, giving a total of whatever the figure is, 14.9 at the end there. So for that particular one motion, that's the value in the database for 9. And as we go through, effectively go through all of the values, you'll either have either P1SE or P1SSE for each of the parameters, right the way up to 999. But you'll see as we go through this, the centimetre column is increasing all the way up to 80, and when we get to 80, that will be the maximum value, depending on whether it's a P1SE or a P1SSE. So let's move on and look at using this data for creating the digital value for MTM-2. Okay, here we are at that part of the application where we can create codes for MTM-2, MTM-UAS or any other MTM system that has been pre-configured. Let me first briefly explain the functionality of this page. Taking it from the top, we have the radio buttons where we select whichever system we're working with, in this case MTM-2. Dropping down a level, we then have a number of drop down boxes from which we can select the appropriate parameter we're looking at. In the case of MTM-2, all we need to do is to select the abbreviated code, GA-GBGC or PA-PB-PC. So let us select, say, GA5. We don't need to bother with case or parameter, because these are already preset in the MTM-2 configuration. All we need to do is select distance, which we'll do from, say, where are we? From 0 to 5, and then we just literally hit run, and that automatically selects all of the values within the MTM variance database, which is the one at the bottom, which is the master table in the database, and there are 1,000 records in there for this particular GA5 code. There's 1,000 records for every other code, both in MTM-2 and UAS. The reason for the 1,000 is for selecting random numbers from 0 to 999 when we come to look at simulations. It's calculated the TMU value of 2.8 and the standard deviation of 0.7. What that means is that the standard deviation of 7 means that one standard deviation, all the values for GA5 will fall within 0.7 TMUs of 2.8 either side. Looking at 95% confidence level, that would require two standard deviations, 1.4. So what this is telling us is that the GA distribution, the ranges within the GA distribution theoretically fall between 1.4, which is 2.8 minus 1.4, and 4.2. Let's have a look at this table here and see whether that's true. The highest value is at the bottom here, the last value in the database, which is 3.4, and the highest value, lowest value, is 2. The TMU values within that, so that range of 1,000 records, is between 2 TMUs and 3.4 TMUs. So in reality, 100% of the records fall within less than 2 standard deviations. Had I have selected show distribution, that would have given me that information there, which is effectively what we just discussed. Before moving on to look at random simulations, we should first look at this summary of the digital calculations for MTM-2. All 39 codes for MTM-2 are shown in this left-hand column. Going across the other columns, the second column we have the data card TMU values. The next column are the digital TMU values. This fourth column is the frequency of occurrence of each of the codes within the 1971 MTM-2 project. These next two columns are included as calculations for the weighted aggregate values of both the digital and the data card values. This final column is the frequency per thousand, and what that means is the frequency per 1,000 motions. For example, if we scroll down the sheet, pick up, let's say, PA 30, that is 100 motions per 1,000, or 10% of all the motions within the project report. Going further on, go down to apply pressure, this code here, you can see that's 84 per 1,000, which is 8.4%. That column is particularly important because it is the source for one of the main tables within the database, which is called the random sets table, and we'll see that in action when we look at simulations. Going to the bottom of this sheet, we can see set out in the blue text here, in this section here, at the bottom here, the average weighted values for both the data card and the digital TMU values. The mean value for the data card TMU value is 12.63 TMUs, and for the digital value it is 12.84. This gives a discrepancy of 1.6%, which is fairly small. However, you will see the impact of that discrepancy when we come to see simulations. Moving on to this second sheet, we can see that the variance is shown for each of the codes. The variance is simply the standard deviation squared. For example, when we were calculating codes in an earlier session, we calculated the TMU value and the standard deviation for the GA5. The standard deviation returned was 0.7 TMUs, so 0.7 squared is obviously 0.49. These last two columns are again aggregation values. What I mean by that, they are the sum of the frequency of occurrence of the particular motion multiplied either by its variance or the TMU value. For example, this cell here is the TMU value for the GA5, that figure there, multiplied by F, which is the frequency, divided by the total frequency for all motions, which is 8767, giving that value there. And the same for variance. It's the variance, 0.49, multiplied by the frequency, divided by 8767 again. By then going right to the bottom of the page, we see the sum totals for TMU value, which is again the 12.84 figure for the mean TMU value, and a total variance of 4.86 TMUs. We'll then take the square root of the variance and divide it by the mean TMU value to give the percentage standard deviation, then by some arithmetic calculation, which you can see up in this little formula at the top of the page here, we arrive at a systematic error, or a system error, at 95% confidence of 606 TMUs. I'm not going to explain that in any more detail because it really is only academic use, because quite frankly it's impossible to arrive at a set of codes totaling 606 CMUs which have the same frequency of occurrence of each of these 39 codes. With that detail out of the way, we'll now go on and see some simulations. Here we are at that stage where we can now run random simulations of any MTM analysis where the codes have been pre-configured in the MTM variance database. Here we have the random sets table that we discussed in the previous session, this table here. And below it is the TMU values table, which has all of the codes for both MTM-2 and for MTM-UAS stored. So at last, the first set of simulations for MTM-2. Fast forward 10 minutes and we can now see the 10 random simulations set out in this right hand grid, this one here. As I scan through it, just notice the first few motions, how they change. Step is the highest one there, PA15, PA30, PA30, PA15, PA30, etc, etc. If I now click this box, we can now see the distribution of MTM-1 analyses for that particular MTM-2 analysis. The red line underneath the chart represents an imaginary line if they had corresponded to the data card TMU value plus or minus 5%. In other words, the data card TMU value for this particular analysis is 606 TMUs, that figure there, and plus or minus 5% of that is from 570 to 636. So in other words, this range of values shown in this chart should have started at 576 and had a maximum of 636. Now if you watch the red line whilst I scroll through the grid, you will have seen that it tends to deviate to the left always, and this is because of the discrepancy between the digital and the data card values. And if you look at the far right hand column over here, the variance between the TMU values is shown, and you can see it is really not very high but significant, between 1, 2 or possibly 3%, and in consequence of that it distorts the distribution. This centre column is headed in range, and that shows the number of MTM-1 simulations that fall within plus or minus 5% of the MTM-2 data card value. 100 simulations was taken for each analysis, and if you scan through the grid, you'll see that in fact only 1 out of 10 achieved 95% or better. We'll now run the same 10 analyses by using the digital TMU values instead of the data card TMU values. So here we go. Fast forward again another 10 minutes or so, and we now have a set of 10 analyses with the digital MTM-2 values. The grid is highlighted at the last data card value, the last one of the previous 10 analyses we ran, and beyond that we now have the 10 digital values. So again, if I continue scrolling down the list, you will see a significance. Again, watch the red line. Notice it maintains a very central position, and that's obviously because there's no discrepancy. which is confirmed by this far right hand column. Every value in there is 0%. So we have no deviation. The consequence is, again scanning through the list, 98 in range, 98, 92, 93, 98, 96, 92, 97, 95, 96. So the direct comparison is that with the digital values, 7 out of the 10 were in range. With the data card value, there's only 1 out of 10. A sample of 10 analyses is a very, very small sample. So what I'm now going to do is run this program for a considerable time, both with the data card values and the digital values, to get a very representative set of samples, and we'll look at the results shortly. Okay, let's now look at the simulations. By clicking on this button here, there we see the random simulations for the data card values for MTM-2. You can see by this box here we've run almost 1400 simulations, random simulations, starting at the low end, 400-500, and going up to the upper level of about 2000 TMUs. The distribution is fairly lumpy, as we'd expect, and when I say that I mean knowing how we had that small 1, 2 or 3% deviation between the digital values and the data card values. Despite this not being a perfectly smooth distribution, let's try to be a bit more precise about the exact systematic error for the data card values for MTM-2. If you examine the chart at the upper level of 2000 TMUs and beyond, you will see that it always returns figures in excess of 95%. For example, 2000 returns 96%, 2100 98%, 2200 TMU 99%, 2300 97%, 2400 100, 25 99, and 26 98. Before going on to look at simulations for the digital MTM-2 values, let's set the TMU value that was calculated in the original 1971 project report. Let's set that value in the program. So we select TMU values and select 1600 TMUs, which is the figure that was recommended. See that there? And let's go. You can see that it's returned in range figure of 91.2%. The count is 34 analyses within the 1600 range. If you examine this grid beneath the frame, you can see that there are only 3 analyses that are not in range. This one, and this one. Hence the 91.2% in range. Now if we select charts here, we can see the MTM-1 distribution for each of those 3 analyses. If I click on that one, you'll see it there. Click on that one there. go back to the first one, and so on. So you can see that each of those three analyses are shown, and in all cases again the red line is drifted, and again in all cases the red line has drifted to the left. To smooth this over a fraction, if I select digital values in the target range frame down at the bottom here and repeat that scan, you'll notice that that red line is very, very central, and all of the values in the MTM-1 distribution fall within that red line. Over now to the digital MTM-2 values, and I've done this simply by clicking on this checkbox here. I've also left the TMU value in the box at 1600 TMUs, and by clicking it we can see that we have a in range of 100% and a count of 58 analyses. If I click summary charts, we see the complete distribution for all of the random analyses. The total number of simulations is just over 4,000, giving us a very, very smooth distribution, as you'd expect. Looking at the section at the bottom where we show the in range for each of the TMU values, you can see that at 1,000 TMUs we have 97% in range. So to return to the frame at the right hand side, if we select 1,000 TMUs in there, let's have a look. You can see that we return 571 analyses, which is a significant and representative range of distributions. Returns 97.2% in range, but we must take account of the standard deviation, which corrects the sample size. A 95%, which is the figure there, will return that set of values. If I increase it to 99%, which is 3 standard deviations, let's see what happens then. We have a standard deviation of 2, exactly 2.0, which effectively reduces the in range figure to 95.2%. I don't propose to discuss any more with this particular set of values, except that it confirms that the systematic error of digital MTM-2 is around 1,000 TMUs, but we'll discuss that in a bit more depth when we go onto motion analysis. You will recall that earlier we calculated values for both MTM-2 and MTM-UAS using this application software. We calculated a number of values, including this PA1, which we ran, returning a value of 5.78, the TMU value, and 2.72 for the standard deviation, and it was entered into the TMU values database, which you see on the top center here. We get the UAS value, which is there, 5578, and the data card value alongside it. We also ran combinations of various UAS codes, and I remember us doing the AA1, which is this one here. We ran that, and we produced a TMU value of 15.0 TMUs and a standard deviation of, variance of 16. So let's now look at the overall summary of these calculations by going to this chart here. All of the calculations are summarized on this chart. We have 9 for place and 18 for combinations of get and place. You may well not have noticed, but there is quite a discrepancy between the data card value and the digital TMU value. It's not as though there's just one or two discrepancies. The discrepancies range across all of the values, and you'll see at the bottom here that the average discrepancy is 29%. The discrepancies are not only large on average, but individual discrepancies from motion to motion are very erratic. To put this into context, let's just compare the discrepancies with the MTM-2 values. The chart shows the range of discrepancy for individual values. The grid here lists the discrepancies in ascending order. First discrepancy being step, minus 16%, going right the way down to this group of values here, which we've categorised as ENW, effective net weight, which are the get weight and the put weight components of MTM-2. But you will see, incidentally, those get weight and put weight are on this far right of the grid, which are the most extreme discrepancies. But you'll see that most of them, more than 70%, are scattered around the 0 line, which is this centre line here, this one here, this one, which is almost 40%. And you've got within less than 5% is 10%, and over 5% is about 25%. So that's the 75% scattered around the 0 discrepancy mark. The cause of that is solely the rounding of the data card values to the nearest whole number, whereas with the digital values they're recorded to 2 decimal places. Let's now look at the MTM-UAS. Woof. Incredible. Obviously it's very disappointing that MTM-UAS displays such extreme discrepancies, but there is little point in running random simulations. Nevertheless, there is a need for a third level system to operate at a level higher than MTM-2. So a new third level system has been configured, and we'll look at that in detail in the next video when we look at motion analysis. I hope you found this first video on digital MTM informative, Any questions or queries, simply email me at digitalmtm@outlook.com and I'll get back to you as quickly as possible.